receiving questions concerning L'Hopital's theorem, so we decided to create a video fully describing this theorem and illustrating it by several examples. When can it be used? Well, suppose you have a limit which involves the indeterminate form of infinity over infinity or 0 over 0. And the L'Hopital's theorem allows to eliminate such difficulties by using derivatives. First of all, a little bit of theory. Suppose you have two functions, f of x and g of x. What we know about them is that their first derivatives, f prime of x and g prime of x, exist in some neighborhood of the point A, except for possibly the very point A. We also know that the limit, as x approaches A, of f of x function and g of x function equals infinity, or the limit as x approaches A of the f of x function and g of x function equals 0. Then, if the limit as x approaches A of the quotient f prime of x over g prime of x exists, it may be stated that this limit is equal to the limit as x approaches A of the quotient of the original functions f of x over g of x. So, basically what the rule says is that if you have a limit to solve, limit of as x approaches A of f of x over g of x, and this f of x over g of x is the indeterminate quotient in the form of infinity over infinity or 0 over 0. Instead of this limit, you might evaluate the limit of f prime of x over g prime of x. But you should always keep in mind that these two derivatives should exist. Well, not should, but they must exist. And this second limit must exist as well, because there can be situations in which this first original limit exists, but the second way doesn't, the second one. Let's take a look at an example, like limit as x approaches infinity of x plus sine sine of x over x. If we plug in infinity, we'll see that we have the indeterminate quotient in the form of infinity over infinity. So we can try to apply this L'Hopital's rule. So we find the derivatives of the numerator and denominator, and what we have is the limit as x approaches the infinity of 1 plus cosine of x over 1, which is the same as the limit as x approaches infinity of 1 plus cosine of x. But this limit right here doesn't exist. So it turns out that we can't use the L'Hopital's rule in this case. So we have to be careful about it. If having applied the L'Hopital's theorem we still obtain the indeterminate form infinity over infinity or 0 over 0, we may apply it one more time, or we can do it as many times as we need until we've reached the acceptable result. While solving the problems with the limits, we can meet the indeterminate products in the form of 0 times the infinity, or the indeterminate differences like infinity minus infinity, or the indeterminate powers like 1 to the infinity, or zero to infinity, or 0 to 0. And these are the forms that can be transformed in the forms of the quotient, infinity over infinity, or 0 over 0. So that we could try and use the L'Hopital's theorem. That's how it goes. Now let's try and solve a couple of problems. Take a look at several examples. First of all, let's find one of the so-called remarkable limits. So it goes the limit as x approaches 0 of sine of x over x. If we plug in 0, we'll obtain the indeterminate form 0 over 0. This means we can apply the L'Hopital's theorem. So we write down the derivatives of the numerator and denominator. And instead of sine, we have the cosine function in the numerator, cosine of x, and the derivative of x equals 1. So this leaves us with the limit as x approaches 0 of the cosine of x, which is equal to 1. Now that's a familiar result, but we've obtained it easily by using the L'Hopital's rule. Let's do a couple more examples. I have them written on the board, so we'll do them one by one. So the first goes the limit as x approaches 0 of ln of x over 1 plus 2 times ln of sine of x. So obviously, this is the quotient of the form infinity over infinity, or to be more precise, negative infinity over negative infinity. So we can try and use the L'Hopital's rule, and to do this we need to find the derivatives of the top and the bottom. So we go, the limit as x approaches 0 of 1 over x divided by 2 times 1 over sine x times the cosine of x. This looks a little messy, so I suggest that we clean this up a little bit. Like this, limit as x approaches 0 of we obtain cotangent right here. Because as we know, cotangent can be written as cosine of x over sine of x. And if we divide 1 by the cotangent, we would obtain tangent. So this leaves us with a tangent of x in the numerator. We still have this 2 multiplier. And x from the top. So again we have 0 over 0 indeterminate form. This means we could either use the L'Hopital's theorem one more time or look closely at this expression to see if we can do anything with it. And I think that we can. I suggest we pull 1 second out front. So this leaves us with the tangent of x over x under the limit, but we can write this thing, this tangent thing, as sine of x over cosine of x, and we still have this x in the denominator. Now, this can be written as follows, as 1 second times the limit as x approaches 0 of sine of x over x. And this is the remarkable limit we have evaluated just a moment ago. And we know that it's equal to 1. And we still have this other limit as x approaches 0 of 1 over cosine of x. So if we plug in 0, we obtain 1 over 1, which is 1. So this leaves us with 1 second times 1 and times 1, which is equal to 1 second. So 1 second is our answer to the first problem. We can write it down right here. Let's move on to the second example. Example number 2, which is the limit as x approaches 0 of 1 minus cosine 4x over x squared. Now if we substitute 0 in this expression, we'll obtain the form of 0 over 0. So this means we can apply the L'Hopital's rule. So we're calculating the derivatives of the top and the bottom and obtain 4 times sine of 4x over 2 times x. And again, we have the indeterminate quotient of the form 0 over 0, so we could use the L'Hopital's rule one more time, or again, we can look closely at this expression to see if there's anything we can do about it. And again, I think that we can, because we can write it in the following way. We can multiply both top and the bottom by 2. So we'll have 8 times sine of 4x over 4x. And this thing right here, as x approaches 0, is again the first remarkable limit. So this thing equals 1. And basically this leaves us with 8. So the answer to the second example is 8. So we're considering this third limit as x approaches 1 of 1 minus x, 1 over x minus 1 minus 1 over ln of x. And this time we have the indeterminate difference of the form infinity minus infinity. This means that we can't use the L'Hopital's rule at once. We need to make some transformation first, and the first thing that comes to mind is to reduce these two fractions to the common denominator, so let's do that. We have the limit as x approaches 1 of ln of x minus x and plus 1 over ln of x times x minus 1. And this time we have the indeterminate quotient of the form 0 over 0. So this means that now we can apply the L'Hopital's rule, and that's what we're going to do. So we have the limit as x approaches 1 of the derivative of the numerator, which goes 1 over x minus 1 divided by the derivative of the denominator, which is 1 over x times x minus 1 and plus ln of x. Now this looks a little messy, so let's clean it up a little bit. And I suggest that we multiply the top and the bottom by x. And we'll have the limit as x approaches 1 of 1 minus x over x minus 1 plus x times ln of x. And again we have the indeterminate form of 0 over 0. And we'll use this rule one more time. So this time we'll have the limit as x approaches 1 of negative 1 over 1 plus x over x and plus ln of x. Now we can take a chance and substitute x into this expression, and we'll see that what it gives us is simply -1 second. So -1 second is our third answer. And we have two more to solve. Limit as x approaches 0 of x times ln of x. This time we're dealing with the indeterminate product in the form of 0 times the infinity. So we can't use the L'Hopital's rule at once, and we have to modify this expression. And I suggest that we do it like this. Limit as x approaches 0, ln of x over 1 over x. And this way we have the indeterminate quotient in the form of infinity over infinity. So now we can apply the L'Hopital's rule. So we'll obtain the limit as x approaches 0 of 1 over x over -1 over x squared. Or if we clean it up a little bit, we'll have the limit as x approaches 0, -x squared over x, which is the same as the limit as x approaches 0 of -x, which equals 0. And this is our answer. So here we have this limit equal to 0, which leaves us with the final one. And the final limit goes like this. Limit as x approaches infinity of x times e to the x over 2 over x plus e to the x. And here we have the indeterminate quotient of the form infinity over infinity, so we can apply the L'Hopital's rule. And we'll go limit as x approaches infinity of, and now we'll take the derivative of the top, so we'll have e to the x over 2 plus 1/2 times x times e to the power of x over 2. And we'll have 1 plus e to the x in the bottom. And if we look at it, we'll see that we still have this indeterminate quotient, infinity over infinity. So this means that we have to apply L'Hopital's rule one more time. And we'll have the limit as x approaches infinity of 1/2 times e to the x over 2 plus 1/2 e to the x over 2 plus 1/4 times x times e to the x over 2, and we'll have e to the x in the bottom. We can add these summands so that we'll simplify this expression a little bit. And we'll have and we can factor out e to the x over 2. So we'll have 1 plus 1 over 4 times x, and we'll still have e to the x in the bottom. Now I suggest that we divided both numerator and denominator by e to the x over 2. So we'll have the limit as x approaches infinity of 1 plus 1/4 of x over e to the x over 2. I believe so. And we can use the L'Hopital's rule one more time, because we again we have this indeterminate quotient. So if we use this rule one more time, we'll have the limit as x approaches infinity of 1/4 over 1/2 times e to the x over 2. And this limit is obviously equal to 0. And that's our final answer. So the final limit is equal to 0. And that's how that's done.